Before we kind of dive back into some logical equivalency stuff, and we'll actually talk a little bit about quantifiers. We'll talk about the for all quantifier and the existence quantifier, which are pretty important in just common language, but they're especially important in mathematics. But one thing I wanted to do was talk about the converse of the Pythagorean theorem, okay? Because I think that this is so interesting that it would be a shame to not cover it. I was going to talk about it on Friday, but then we had a network issue, which we thankfully corrected, thanks to Monique. But let's go ahead and talk about the converse of the Pythagorean theorem. So here's what is assumed. So the converse is that if you have a triangle that satisfies the Pythagorean equation in terms of lengths, that is that the square of one of the legs is equal to the sum of the squares of the others, then that triangle must be right. Okay? So the converse, let me just kind of write, I'm going to actually annotate in here, okay? So the converse says, so in this little picture right here, which is basically driving the proof forward, Euclid actually gave this as well, okay? Says that if the length of BC squared is equal to, the way he set this up was just, assume that one of the legs is equal to the sum of the squares of the others. The length of BC squared equal to the length of AC squared plus the length of AB squared implies what? Yeah, triangle BAC. I always like to put the right angle, triangle BAC. Now, I mean, what will fall out of this is that actually angle A or BAC, angle BAC is necessarily going to be a right triangle, since BC is kind of our hypotenuse. It's the long side, the way that we've written this. Implies triangle BAC is right. Okay. And here's what Euclid did. Okay, I'm just going to say it in words, and we'll kind of sort this out together. So the first thing he did was he drew triangle BAC, and he assumed that the square of BC was equal to the sum of the squares of the other two legs, as we've written here, yeah? And notice that he hasn't said anything about angle BAC. He's just said, look, it's an angle in this triangle or whatever, yeah? So I haven't labeled it as a right angle or anything of that sort. Then what Euclid did is he pulled out his compass and straight edge and started constructing stuff, okay, as the Greeks were prone to do. And immediately he went to that point A right there, and he created in particular the segment AC, okay? And he created a perpendicular to the segment AC, okay? That's why you have this right, you see that right angle right there? That would have been child's play for the Greeks with their compass and straight edge. So he said, construct a segment that just extends indefinitely from the point A away from AC that happens to be perpendicular, yeah? Then what he did is he took his compass and kind of placed the point of the compass on point A and extended it out to point B, and he did this. You know what I'm saying? So this point D right here is a radius of that circle that he would have made with the compass. Therefore, what would be true about AB and AD? They are congruent. Yeah, so they're the same length. Okay? Obviously, okay, so I'm kind of staring at triangle CAD. So here's the claim. The claim I'm going to make is that triangle CAD, right? Triangle CAD is congruent, you guys know that little symbol for congruence. All right, equals, because equals means they're exactly the same thing. But congruent means that they have all kind of parts that correspond to one another. Is congruent to triangle CAB. Oops, CAB, CAB, okay? That's the claim that he's trying to establish. Now, the first thing he gets is that AD is the same as AB, okay? Clearly, AC is congruent to itself, yeah? And finally, what about the last side? Now look, I'm trying hard to not reference any angle measures. I'm trying to establish congruence through side, 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 if possible. I have two sides so far. It wouldn't, you know, I could try to go for side angle side congruence, but that would cause me to have to reference the angle that I'm trying to figure out stuff about right now. Namely that angle CAB or BAC or whatever it is, yes? So the better approach is to actually try to say something about the third side of these triangles, okay? Yeah. So what do you guys think? What do you think we could do? Yeah. Yeah. That's right. That's right. So first of all, AD and AB are congruent. AC is congruent to itself, obviously. Yeah. So that's exactly the argument. So watch this. If I look at AD squared plus AC squared, then clearly this is the same thing as AB squared plus what? AC squared, which is by assumption, and I'm going back over here, by assumption, that's just BC squared. Do you see what I'm saying? Okay. So that's equal to BC squared. I'm gonna, all right, yeah, that's equal to BC squared. But also, what's AD squared plus AC squared equal to? This is kind of the surprise in his argument. It's equal to CD squared. By what? What did I just use? Because this is a right triangle. Do you understand what I'm saying? What does he use in the reverse direction? If you have a right triangle, then the sum of the squares of the legs equals the square of the hypotenuse. That he uses the Pythagorean theorem in the reverse direction. So this is by PT, the Pythagorean theorem. So look at this. You see it? CD squared equals BC squared. Do you see it? So what does that tell you about CD and BC? They're the same length, yes? Right, so let's say CD is equal to BC. So what's true about the triangles? Triangle CAD is congruent to triangle CAB by what? Which kind of congruence are we using here? Side, side, side. But CAD is a right triangle by construction. So what's true? So CAB is right. Is right. Exclamation point. That is the end, right? And that's that. I mean, that's the totality of his argument. Basically, this picture kind of encapsulates everything. Does that make sense? This is so it's a logical. This is appropriate here. It's a logical equivalence. It's an if and only if, right? Triangle is right if and only if we were able to go both directions. If and only if the sum of the squares of one leg is equal to the sum of the squares of the other two legs. Okay, I see lots of hands going up here. So yes, Monique, yeah.
That's not a right triangle. I'm confused.
Well, the picture is sort of misleading. I mean, right, he kind of drew it so that it didn't have to be necessarily. Does that make sense? But he's there, the way he's drawn it, he's like, okay, potentially this angle CAB might not be a right angle. But then we discovered in the process of creating this other thing, that indeed that angle is right. So don't let your eyes deceive you, right? Logic dictates that that angle right there is actually a right angle, okay? Whether it looks like it is or not. Which dash?
Like the line on AB, all you would have to do is erase that, and then this proof is.
Yeah.
But
Yeah.
Because it's there.
Uh-huh.
Then it's the right.
Yeah. So technically, the way that we drew it, like logic dictates that the way we drew this thing, the way it looks, is inappropriate. Does that make sense? Technically, that line should kind of come down a little bit, and you should have a right angle. Does that make sense? Okay. I mean, we made an argument that sort of dictates that has to be the case. Okay, other questions? Other questions? Well, I think that's pretty cool. And I mean, I do care what you think, but frankly, I'm not going to let you rain on my parade, okay? I think that's pretty awesome. I'm going to feel pretty good for the rest of the day thinking about that, okay? And if you don't, well, what hope is there for you? That's an awesome proof, I think, okay? What am I doing here? I need to erase this junk here. Let me clear this, and we will go do some other stuff. So any other questions before we move on? Other questions? Well, let's do it. Okay. So last time we talked about these key logical equivalences. I mentioned how these things, and remember when we talk about logical equivalence, we use this sort of triple equal sign looking thing, yes? Because I mean, it doesn't really make sense to use equals because we're not talking about quantities here. We're talking about logical statements, yes? Okay. And again, all these slides are uploaded to, the slide module in Canvas. And by the way, let me just ask, I'm pretty sure I published everything now. Should have access. Did people check on that? There was an issue last time, but I'm pretty sure all that should be accessible now. We had the identity laws. I said some of these were acting like addition and multiplication with like ones and zeros, which is the way that you'll see it in digital logic design if you happen to take that class at some point. Domination laws, P or true, that's automatically true, right? That makes sense. Whatever P happens to be, if you OR it with a true, it will automatically be true, yeah? The idempotent laws, the double negation law, the negation law, P or not P, that's obviously true. That is, okay, we had another logical term for statements like that, like P or not P. We used another statement for that. It's always true no matter what P is, and therefore we call that a tautology. On the other hand, if I change the or to an and, that's a contradiction, yeah, okay? And we had all these. There was the commutative laws, the associative laws, the distributive laws. I have some stray parentheses. Sorry about that, but I have an opening parenthesis that shouldn't be there on both those distributive laws. Absorption laws, okay, we talked about why those happen to be the case. And I have a few other key things that are just nice to have in your cognition. So we've talked about the fact that P implies Q is equivalent to not P or Q. Didn't we talk about that before? I gave the example of you better eat your vegetables or you're not getting dessert, yes? And we talked about why that's equivalent to an if-then statement, just intuitively, okay? P implies Q is equivalent to not Q implies not P. What's that called? P implies Q is equivalent to not Q implies not P. Do you remember? We had a name for that. It was back here. Oops, where was that? or it was, no, I thought I had it in here. It was the contrapositive. Maybe that was in the last slide presentation. Sorry. Okay, so that's the contrapositive. Okay, so I say if you get an A in the class, or if you get an A on the final, then you get an A in the class. That's equivalent to me saying if you don't get an A in the class, then you must not have gotten an A when on the final, right? Those are equivalent things. And I'm not necessarily expecting you to memorize this whole table, but I do want to zero in on a couple of these, okay? So look at this. Stare at this guy and this guy, okay? See those two right there? P implies Q is equivalent to not P or Q, right? And not P implies Q is equivalent to P and not Q, all right? Now, intuitively, that second thing makes good sense. Here's why. If I say, if you get an A on the final, then you get an A in the class, what would be the logical opposite of that? Think about it. I say, so I make a verbal contract to you. If you get an A on the final, then you get an A in the class. What would be the logical opposite of that? Yes. That's right. That would be the opposite of what I said, yes? So you get an A on the final and don't get an A in the class, yes? So it makes sense that the opposite of P implies Q is P, that is you get an A on the final, and not Q, you don't get an A in the class. Does that make sense? Okay. But there's a connection between these two that I'm hoping you'll see what the clear connection is. What about the things that are sitting on the right-hand side here? You actually know that those are equivalent. How? Do you guys remember that we learned another law? De Morgan's law says that if you take the negation of not P or Q, then what you can do is just take the negation of each thing and change the or to an and. Yes? Okay, it's the same thing as not P. And what? Not Q. But what's not P? P. So this is equivalent to, oops, I'm using equals. This is equivalent to P and not Q, which is exactly what you see down there. Does that make sense? That's a good one to keep in mind. Okay? There's some in here that just make perfect sense. So for instance, let me see here. I thought there was, okay, actually some of these are a little bit tricky. Okay, so I'm going to write down one that I don't see on here, but that I think you should probably be able to tell me what it's equivalent to. So suppose I have P implies Q and Q implies R. What do you think that is? Or so P implies Q and Q implies R. Yeah. Okay, so you think that that's equivalent to P implies R? You think it's equivalent to P implies R? Let's okay, so okay. So let's put a question mark on this. Okay, a question mark. Is this equivalent to P implies R? Okay. So why don't you work with your neighbor on that and see if, do you know how to check whether these things are logically equivalent at this point? What do you have to do? You have to do sort of a truth table. Does that make sense? Now, in this one, it's going to be a little bit trickier because why? How many variables are involved? 3. So it's not just 4 possibilities, it's 8. Yeah? It's 8. So what are the 8 things going to be? Can you guys see this? So PQR. Can you guys see that? Yeah. Oh, it's over there on the left. Yes. Okay. So look at this. True, 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 true. False, 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 false. How about true, false, true, false? Or no, true, true, false, false. True, true, false, false. And then what do you think I'm going to do with R? True, false, true, false. True, false, true, false. Okay. So work on that for a minute. Okay. Write down P implies Q, Q implies R, the and of those things, and then write down a truth table for P implies R. And what had better be true? If these are indeed equivalent, what had better be true? Yeah, well, not necessarily a tautology. It should just, the truth values should be exactly the same if those two things are equivalent. Does that make sense? So work on those for a minute with one another. Okay. Okay, let's fill some of this stuff in. I know I see some people starting to look up. So the implies is pretty easy to fill out a truth table for. If it starts with a false, it's true. Yeah? Remember, if the premise is false, the whole thing will automatically be true. So I can immediately say in the P implies Q column, I can immediately say what about these last four things? True, 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 true. That's exciting. Okay. And then the true implies false. That's the only time we get false, right? And then we have true, true. What about Q implies R? Okay, we're with the ones that start with false, I immediately write down true, yeah? Then I have these four other situations. Okay, the ones that started with false, I automatically write true. And I have these four other situations. This one's true. The true implies false is false. Okay, and then what? True implies true, true. True implies false, false. And then I called them A and B just for simplicity. Okay, so if I add these things together, this is easy. True, false, 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 true, false, right? I have to have both true to get true, yes? Okay, so I have four falses and four trues. What about P implies R? If I start with the ones that start with false, which are the last four for P implies R, those are automatically going to be true. So what do we immediately conclude? Yeah, they're not equivalent, but something, right? So they're actually not equivalent right now, but let's kind of finish the job here, you know, let's not horse around. Okay, so true, 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 true. Okay, and then what about the other one? So P implies R, true, false, true, false. Is that what that is? Okay, interesting. So they're not equivalent, but it seems like something should be true, right? There's some kind of connection here, and it turns out that there is, and it turns out that what's burning in the back of our mind when we think about this has to do with an argument that we would make. It's not that these are equivalent, but it's an argument that we make. Namely, if P implies Q and Q implies R is true, that implies that P implies R is true. Does that make sense? That implies that P implies R is true. What we have in the back of our mind is something that's going to end up being a tautology, something that's always going to be true, and therefore it's going to be a valid form of argument. If I say, hey, if you get an A in the class, or if you get an A on the final, then you get an A in the class. If you get an A in the class, then I will give you a gold star. Then what would you conclude from that? What would that imply automatically in your mind? If you get an A in the final, then you will get a gold star. Does that make sense? So what you're detecting in the back of your mind is a form of argument, not a logical equivalence. Does that make sense? But we will kind of look at that pretty soon. So, but that's good that you've detected something. There's something there, right, that we just know with our logical intuition. Okay? All right, let's move on. Okay. Look, there's some funny notation. Sometimes we have multiple ors, okay? And so we'll oftentimes shorthand notation it kind of like the way you would in like a calculus problem, actually. You'll put an or with like j going from 1 to n, and that just is understood to mean P1 or P2 or P3 all the way up through Pn. Does that make sense? And same thing with the and notation, okay? There's a giant, and sometimes you'll even write things like this. You'll suppress this junk that's sitting right here. And you'll just say, you'll just write or the PJs, right? And you'll just put a little J on the bottom. That means you just go over all possible J's. Does that make sense? Or down here, we'll just write and you put a little J on the bottom, PJ, and that just means, hey, just and together all the PJs. That makes sense, like P1 and P2, etc. Okay? Any questions on that weird notation? It's just shorthand. It's convenient. Okay? By the way, let me ask you something. What if I negated the or over a bunch of j's? I don't care how many there are. PJ. What would that be logically equivalent to? And over j, what? Not PJ. What did you just use? Yeah, that's De Morgan. Okay, De Morgan. And similarly, you could do that with the ands as well. If you negate a bunch of ands, that's going to be the or of a bunch of not of those things, yes? Okay, so in other words, not and j, PJ, this is equivalent to or j, not PJ. Yeah? Yep, that's right. That's exactly right. Yes. Yeah, it's just an extension of the De Morgan law. Yes. We saw it in the case of 2, but it also works for any number of them. Okay. Any questions on that? It's important. Here's something to work with your neighbor on. Show that that thing is logically equivalent to that other thing. Okay. By using some logical equivalences. Okay, show that that complicated first thing is equivalent to that less complicated second thing. That make sense? And what I would recommend, actually, let's do this one together. Why not? Okay, so not, seems like it's best to kind of start with the more complicated thing. Not P and Q like this. Okay, I say we use De Morgan's first. And if I use De Morgan's, what's going to happen? Okay, not P and what? Not, not P and Q. You see that? Now, what does it seem like a next step would be? That was De Morgan's law, right? So DM, De Morgan. I can do De Morgan on the second thing as well. Know what I mean? Okay. So this is logically equivalent to not P. I'm going to sort of suppress the parentheses because it's not, you know, vague what that not symbol is referring to. Okay, not P and, okay, what's this next thing going to be? Right, because not P is P. P, and let me just do this. P, now I really do need to use parentheses. P or what? Or not Q, yeah? Now, what do you think I'm going to use next? Well, yeah, all right. So De Morgan got used there again, right? What do you think we're going to do next? Yeah, distribute. Distribute this guy here and here. Do you know what I'm saying? Okay, so here we go. Let's do that. Oops, I turned off my pen. Okay. So this is going to be equivalent to not P and P. Okay, that's interesting. Okay, not P and P, or what? Not P and what? Not Q. Ah, oh, and then what? Well, you can do it, but it's always what? That's a contradiction. Yes. So this thing right here is always not P and P is always false. So I have false or not P and not Q. Yeah. But if you have false or something, then the thing that determines the truth value is the other thing. Yes. False isn't really contributing to the overall truth value. It's the other thing that's going to determine the truth value. So this thing is automatically not P and not Q. Yes? Interesting. So we just used a variety of rules. And so look, we actually have shown this to be equivalent just by using the rules that we know. We didn't even have to make a truth table. Making a truth table for this would have been a wicked exercise, yes? Probably wouldn't have been that bad, honestly, but it would have been fairly tedious. And what we just did was we did it through just thinking about logical equivalences. Any questions on that? All right. That's cool. Now, this is what I was just talking about. We realized that the end of the first two things was not, the end of the first two things was not equivalent to the last two things. But can somebody read off, did somebody write this down? Can somebody read off what the truth table was? P implies Q and Q implies R. What was the truth value or the truth table values for that? Does somebody have those written down? True, false, false, false. Okay, we had this from before, okay? And then what about P implies R?
True, false, true, false, true, 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 true.
Okay? So just for ease of writing this down, I'm going to call this A, and I'm going to call this B. So we want to look at A implies B. Yeah? So what about A implies B? What's the first thing? True. False implies false. True. False implies true. Anytime I see false, true, right? First thing's false, it's automatically true. And then it's true, false, true, True, true. Therefore, what is this? It's a tautology. Now, something that's a tautology means it is a valid form of inference. It's a valid form of logical inference. It's a valid form of drawing a conclusion from previous information. So just like I said, if you get an A on the final, then you get an A in the class. If you get an A in the class, then you get a gold star. You would infer from that what? If you get an A on the final, then what? You get a gold star. What we just showed is that is a valid form of logical inference, even though we already kind of knew that in our own mind. Yes? But it is a valid form of logical inference. A tautology is something that kind of, if you have an inference you're asking a question about, like this one, this is showing that is a valid form of logical inference. Yes.
So that equation there,
Yeah.
how would you know what I forgot the
Implies.
Would that be for the first two sets?
Yeah, right. Yeah, right. It's that. Because remember, and has preference, operational preference over the implies symbol. Does that make sense? Okay. Yeah, other questions? If you're ever unsure, you can just slap parentheses around stuff or something, right? So parentheses will make. Yeah. So because here it's not ambiguous. You don't have to, just because and dominates the implies symbol. Yeah. Good question. Other questions? I want to at least start introducing propositional functions, right? This falls into the category of logic. Logicians, I'm just going to tell you guys, logicians kind of have a little bit of a chip on their shoulder, okay? They like to create these terms that intimidate people, okay? So they'll say, you're not really talking about first order logic right now, okay? You're talking about something else. They'll say things like that. But what we're talking about right now falls into the category of propositional logic, okay? And we're going to start talking about predicate logic. Now, predicate logic is where you have propositions that depend on a variable. And you don't know the truth value of those until someone tells you the variable value. Does that make sense? Okay. So a propositional function, I like to call them open sentences because they're kind of open-ended until you know the value. An open sentence actually is a technical term in logic. They're a generalization of propositions. So P of X, okay? So P would have been a proposition, but it depends on the variable X. Okay, and the P part, so the stuff that doesn't involve the variable X, you call that the predicate, okay? The predicate of the proposition, of the open sentence, okay? So P would be all the words that don't have like the X in it. Like you can understand all the words, but the X thing is what's going to ultimately determine the value, the truth value of that open sentence, okay? Propositional functions, or open sentences, if you will, become propositions, i.e. have truth values, when their variable is replaced by a value in the domain U. You're always operating in some domain U. It doesn't have to be numbers. You could be talking about women. That could be your domain, yes? Men, human beings, dogs, right? Whatever it is, you define a domain. But it could also be integers or rational numbers or real numbers or complex numbers, whatever it is. There's a domain. The reason you call it U is because it reminds you of this is the universe within which I'm actually operating right now. Does that make sense? Yeah? Okay. So, and by the way, Propositional functions, i.e. open sentences, don't just have to have one variable. They could have lots of variables. Okay, so here's one. R of x, y, z is that the sum, I mean, you can, the predicate part is I can just talk about what this is asking me to do. The sum of x and y is equal to z. So the predicate part is everything that doesn't involve the variables itself. Okay. So, and u in this case, for each one of the variables is just the integers. What would the truth value be for x equal to 2, y equal to -1, and z equal to 5? What would the truth value be for this? That's definitely false. Is 2 plus -1 equal to 5? Crying out loud, it is not, right? So I would have the truth value false. Okay. Is 3 plus 4 equal to 7? Yes, so that would be true. Yes. Is x plus 3 equal to z? That is still what? That's still an open sentence. So we don't know yet until someone tells us what x and z are. Does that make sense? Okay, so I'll say this one is still an open sentence. It's a propositional function that we do not know the value of. Okay? I'm going to stop here in a minute, but what about this? P of x is the propositional function x greater than 0. Find the truth value of this. Okay, so first of all, what's the truth value of P of 3? That's true. What's the truth value of P of -1? What's the truth value of true implies false? Yeah, there it is. Any questions on that? Okay, we'll come back tomorrow and we're going to talk about existential and universal quantifiers and how those help us in the realm of dealing with open sentences. Okay.